let's look at how to solve a combustion analysis problem. And this is a type of problem, usually it's a combustion reaction, though it does not have to be, that you have to figure out the empirical formula of a compound, not given the percent by masses of each element that we're used to seeing, but rather giving you masses of products and reactants in a reaction. So your goal is to try to take this data and to, from it, isolate the mass of each element that's in your unknown compound. And to do this by looking at the masses of the products of where they're ending up. So let's look at what I mean. Let's look at this example. An unknown alcohol contains the elements carbon, hydrogen, and oxygen. When 0.510 grams of this alcohol is burned in air, it produces 1.122 grams of CO2 and 0.612 grams of H2O. Determine the empirical formula. So notice that I have written here kind of a skeleton reaction of what's happening. This unknown alcohol contains C, H, and O. So I put CXHYOZ because I don't know the subscripts. It's reacting with air, which is this is where it's pulling the oxygen from. And it's giving me CO2 and H2O. Now in past problems, again, I would have given you maybe the percent of carbon, the percent of hydrogen, the percent of oxygen, and from that you would figure out the empirical formula of this compound. But here I'm giving you entire masses of products and a reactant in this reaction. So let's try to trace how I can find the mass of each individual element in this compound, and we can do that by seeing where these elements are ending up. So what I mean is, if I look at this reaction, all the carbon from the alcohol is ending up in CO2. There's no other products that contain carbon. So what I can do is I can take this 1.122 grams of CO2, and from it I can isolate out just the mass of carbon. And that mass of carbon should be the same mass that I'm starting with in my reactant based on conservation of mass. Can I do this for any other element? Looking at the hydrogen, all the hydrogen is ending up in the H2O, in the water. There's no other product that has hydrogen in it. So if I take this 0.612 grams of H2O, from it I can isolate just the mass of hydrogen, and that mass of hydrogen should be the same mass of hydrogen that's in my starting alcohol. And notice I keep saying isolating apart from a whole thing. This would be helpful to watch the video that I made on using percent by mass as a conversion factor, because that might come into play in this type of problem. So I definitely suggest watching that first, and also watching the video where you can find the empirical formula given initial mass data in terms of percent by mass. Okay, now you might be asking yourself, what about the oxygen? The oxygen is going to more than one place. And it's also coming from more than one place. It's coming from the air and it's coming from the alcohol. So you might have one element that's going to be tricky to trace. But if you can find all the others but one, that last one should actually be easy to solve for. So in this case, if I can calculate the mass of C isolated from the CO2, and I can calculate the mass of hydrogen by isolating it from the H2O, and if I go back to the problem and I notice they give me the initial mass of the alcohol itself, then I can actually find the mass of the last unknown, the oxygen, by subtraction. And this might not always be a combustion reaction. So every now and then you might have different types of reactions you're dealing with, but you're going to go about it the same way. You're going to trace each element that's in your unknown into a product, see, hey, where is it ending up? Is it ending up in only one place? And if it's coming and ending in just one place on either side, then I can isolate the mass from that particular product. Okay, and if there's one that's left over that I can't do that from, then I can do it from subtraction. Okay, so I roughly listed your steps here, calculating grams of C from CO2, grams of H from H2O, then getting O from subtraction, and then once you have the mass of each individual element, then you can treat it like any other empirical formula problem that we've tackled before. Okay, so how do I isolate the grams of carbon from the mass of CO2 that they gave me? There's more than one way of doing this. So for instance, they give me 1.122 grams of CO2. If I wanted to, I can mole it out first using the molar mass. For every 1 mole of CO2, there's 44 grams of CO2. So grams of CO2 left out, and I'm in moles. But I don't want to be in CO2, I want to be in carbon. So then I can say for every 1 mole of CO2, there's 1 mole of carbon, because there's a subscript of 1 for C. And now that I'm in moles of carbon, I can get into mass of carbon. For every 1 mole of C, there's 12 grams of C. I find this way a little tedious. Okay, if I'm looking at it from a direct standpoint, if I'm starting with the mass of CO2, I want that in the denominator of my conversion factor, and I want to end with the mass of just carbon. I want that in the numerator. Oh, hey, look, this is mass of part over mass of whole. This is just using percent by mass as a conversion factor. For every 44 grams of CO2, that's the molar mass of CO2, there's 12 grams of C, that's the molar mass of C, and I get the same answer. So there is more than one way of going about doing this. I prefer the bottom way if I need to get into grams of that one part. And this is why I said you can also look at my video on using percent by mass as a conversion factor. Okay, now I can do the same thing isolating hydrogen from the H2O. Okay, so if I take my 0.612 grams of H2O, again, there's more than one way of doing this. I can mole this out to get moles of H2O, and then from moles of H2O, get moles of H. For every 1 H2O, there's 2 H's. And then I can mass this back out. For every 1 mole of H, there's 1 gram. And I get 0.0680 grams of H. But I find this more tedious. If I'm looking at this from a dimensional analysis standpoint, I want grams of H2O on the bottom, so it cancels. I want grams of hydrogen on top, so I end with it. This is just mass percent. For every 18 grams of H2O, there's 2 grams of H. So there's my conversion factor, and if I calculate this, I get that 0.0680 grams of H. Make sure you keep enough significant figures here, because that will help you get better whole numbers by the end of your process when you get to your formula. Now I've got the grams of hydrogen and the grams of carbon that are in my alcohol, since they were traced from only one place. And I'm just left over with finding the oxygen. Well, that's through subtraction. Okay, I take the entire mass of the sample they gave me to start with, and I subtract out the combined mass of carbon and hydrogen. And if I do that, I'm left with 0.136 grams of oxygen. And now I've successfully isolated each mass of each element that's in my alcohol, and now I can treat it like any other empirical formula problem that we've done in the past. I have masses of each. I don't want masses because the subscripts are on a mole basis, so I've got to convert into moles. Okay, so I take each mass and I mole it out separately. Make sure you keep enough significant figures. These are essentially my subscripts, but now I have to get them into whole numbers, so the best way to do that is to divide by the smallest. If I do that in this case, I get straight to whole numbers C3H8O. And again, I would find it helpful to visit my video on finding empirical formulas, which will elaborate on these last few steps.